Section 1.9 Inverse of matrices. First, definition. We say A and B are inverse if they satisfy the multiplication AB is equal to the multiplication BA equal to the IN. This is the identity matrix with size n. Well, I will explain what the meaning for this matrix with examples. First, for example, I2 is a matrix with size 2 by 2. How do I know that? Well, you have to pay attention to the subscript we have here, this one. Yeah, always it's going to have the same number for the rows and for the columns. So I2 is 2 by 2. It's a matrix that has only, in the main diagonal, it has only 1, and the other entries, they are only 0. For example, I3 will be what size? 3 by 3. Only 1 in the main diagonal, 0 in the other entries. And so on. I4, I3, I5, I6, it is like that. It's a square matrix. Square matrix. Same number of rows and columns. So we say that A and B are inverse if they satisfy times B is equal to B times A equal to the identity. By the way, A and B, of course, must be square and of the same size. So the concept of inverse only applies to this kind of matrices, square and when they have the same size. A square, remember that they have the same number of rows and number of columns. So when the multiplication of two square matrices, A with the same size, AB, you have A times B equal to B times A equal to the identity, then we say that A and B are inverse. Now, if A and B are inverse, we can write B is equal to this. I know that it seems like an A raised to negative 1, but no, we haven't defined something like that here for matrices, but this only means inverse of A. So again, this is the definition to verify that two matrices are inverse one to each other. We need to have the two matrices. Examples. Verify that and B equal to so we have to verify that these two matrices, they are inverse. So I have the matrix A and the matrix B, so I need to make the multiplication. A times B is equal to 1, 2, 3, 4. Remember, we're doing the multiplication of matrices. Yeah. Go to the video in the section 1.5 and 1.6 if you haven't checked that, so you can know how to do the multiplication of two matrices. So we have -2, 1, 3 over 2, and -1/2. So these matrices, they have size 2 by 2. So notice that they have the same size, but they are square besides that. So the concept of the inverse makes sense. So the result is going to be a matrix with size 2 by 2. So here I need to multiply row 1 times column 1. 1 times -2, -2. 2 times 3 over 2 is 3 plus 3. Here, row 1, column 2, row 2, column 1, row 2, column 1, 3 times -2, -6, plus 4 times 3, 12 divided by 2, 6. Here, row 1, column 2, row 1, column 2, 1 times 1 is 1, plus 2 times -1/2 is -1. And here, row 2, column 2, row 2 in the first matrix, column 2 in the second one, 3 times 2 is 3, 4 times -1/2 is 2. So I have 3 minus 2. And then you simplify, and we have 1, 0, 0, 1. And this is the identity matrix with size 2. So yes, they are inverse. Well, I'm sorry. I just did the multiplication A times B. We have to verify that B times A is the same. You can do that. Verify B times A is the same, is equal to the identity with size 2. And then they are going to be inverse. So again, with this definition, you need to have the two matrices. You need to have the two matrices to verify that they are inverse. Then, since AB is equal to BA equal to I2, A and B are inverse. Or we can write A is equal to 1, 2, 3, 4, and the inverse is the matrix B, -2, 1, 3 over 2, and -1/2. Part B. Show that the identity matrix with size 2, 1, 0, 0, 1, is its own inverse. How can we verify that? Well, again, due to the definition we have for inverse is that the multiplication of the two matrices AB and B times A in the two ways must be the identity matrix. So if I'm saying that this is its own inverse, then I need to multiply I2 times I2 times itself, and I should get I2. But it's going to be the case because we have 1, 0, 0, 1, times 1, 0, 0, 1. And we have row 1, column 1, 1 times 1, 1, 0 plus 0, 0, so we have 1. Next, row 2, column 1, row 2, column 1, 0 times 1, 0, 1 times 0, 0, so we have 0. Row 1, column 2 here, row 1, column 2, 1 times 0, 0, 0 times 1, 0, 0 plus 0, 0. And finally, row 2, column 2, 0 times 0, 0, 1 times 1, 1, 0 plus 1 is 1. So notice we have the identity matrix with size 2. So this verifies the definition. This multiplication, this matrix times this matrix, and obviously if we switch the order, yeah, we'll have the identity with size 2. So I2, then I2, is its own inverse. Other example, show that we have to show that this matrix has no inverse. So in this case, we will assume the inverse exists. So I want to say that the inverse is A inverse. I'm going to use some numbers, some letters, A, B, C, D. So if this matrix is the inverse for this one, then they must satisfy A times A inverse is equal to the identity. This implies that 1, 2, 3, 6, 1, 2, 3, 6 times A, B, C, D should be equal to 1, 0, 1, 0, 1. Yeah? Yeah, because this is the definition. If this one is the inverse, then this should be true. So now I'm going to make the product of these two. This implies, check the product for this one. Row 1 times column 1, 1 times A to C, A plus 2C, A plus 2C. Here, row 1, column 2, row 1, column 2, B plus 2D. Here, row 1, row 2, column 1, 3A plus 6C. And finally here, row 2, column 2, 3B plus 6D. And this should be equal to 1, 0, 0, 1. Now, this implies A plus 2C equal to 1. Yeah, remember that if two matrices are equal, yeah, if two matrices are equal, then they are equal entry by entry. So this should be equal to this should be equal to this, B plus 2D should be equal to 0, 3A plus 6C should be equal to 0, and 3b plus 6d should be equal to 1. But notice, in this system of equations, we're going to have one contradiction. For example, notice this one. I mean, not a contradiction. I mean, it won't have any solution, because we need to have a plus 2c equal to 1, but 3a plus 6c equal to 0. But that's impossible to satisfy the two equations, because from this one, multiply the equation 1 times 3. This implies 3a plus 6c equal to 3. I multiply the equation 1 times 3. 3 times a, 3a, plus 3 times 2c, 6c, 1 times 3 is equal to 3. But I have the same here, you see that? I have 3a plus 6c equal to 0. So one solution for these two equations, I mean, is one side of the equation equal to two different numbers. So this is impossible. So this is impossible. So it has no solution. No solution. So if no solution, then A this matrix A 1, 2, 3, 6 has no inverse. Yeah, in many problems where you have to find the inverse, you're going to end up with a system of equation like this. So again, in this case, we wanted to show that this matrix has no inverse. I assume that there was an inverse, and then I multiply and set this equal to the identity with size 2, because this is the definition. And then I observed the system of equations. I didn't even have to solve it. Why? Because I observed that in two equations we have a contradiction, so, or something impossible. We have this leads to one equation, one side of the equation, 3a plus 6c equal to 3 and equal to 0 at the same time. So it's impossible, right? Because this implies 3 equal to 0. So this has no solution. Then this one has no inverse. All right. Now, how to the previous definition is only about how to verify that two given matrices are inverse. But now, how do we have a process to find the inverse for a given function, for a given matrix? How we can know that? And of course, how to know that there is no inverse. All right. So here the process. This is manually. I would show you later that you can verify the inverse by using a Webpage calculator for inverses, but manually should be how to find the inverse of a matrix. A of size n by n. Remember, this only applies to matrices with size square matrices, the same number of rows as columns. So first, create the matrix of size 2 by 2n given by do we have to create this matrix? It's going to be a bigger matrix. We have to use the matrix A and assign the identity matrix with size n. Number 2, apply row operations to reduce the matrix. I mean, this is essentially the method of Gauss-Jordan. The same operations we learned there is what you have to apply here. Number 3, if you arrive at the matrix like identity in this size and B in the other one, then B is the inverse. So the purpose with this method is that we can turn this side of the bigger matrix into the identity matrix with size n. If we can be able to do it, then this one here is going to be the inverse. If not, then we don't have any inverse. Note, if at some point when using row operations you see in the left side of AN a row with only zeros or 2 rows equal, then stop. The matrix A has no inverse. Of course, I'm going to show the examples about this, right? But essentially, these are the steps. So I'm going to do some example. First, simple example. Find the inverse. Find the inverse of 1, -1, -1, and -1. All right. So we start with a matrix with size, a square matrix with size 2 by 2. Is that okay? Size n by n, in this case n is equal to 2. Step number 1, we have to create this matrix with size 2 by 2n given by A and the identity matrix. So in this case, the IN is going to be I2 because this matrix has size 2 by 2. So we create 8 I2, which is write the matrix A 1, -1, -1, -1, and here write down the identity matrix with size 2. This is going to be 1, 0, 0, and 1. You see? Now we have to apply row operations. We need to turn this side into this side. First, I will turn this into 0. The first operation I can do is row 1 plus row 2 will replace row 2. If you want, you can say that this one is going to be the pivot. So what do we have here? We will have row 1 plus row 2, 1 minus 1. All right, first, I'm sorry. The row 1 as it is, so 1, negative 1, 1, 0. 1, negative 1, 1, 0. But now we have a new row 2. Row 1 plus row 2, 1, negative 1 is 0. Negative 1 plus negative 1, negative 2. 1 plus 0 is 1. And 0 plus 1 is 1. Notice, now we already have 0 here. Now we need to remember we need to have the identity matrix in this size. So now we need to turn this into 0, the number in this position here. So what can we do in this case? I think I can multiply. Oops. I think I can multiply row. This is going to be a new pivot. So I think the operation could be row 2 minus twice row 1. And this would replace row 1. So I can cancel this. This one, 0. Because I have negative 2. If I multiply this times 2, I will have negative 2. Negative 2 minus negative 2, they cancel out. So in this step, the row 2 as it is, so it's going to be 0, negative 2, 1, and 1. But now I have a new row 1. So I'm going to do it. 0, 2 times row 1, 2 times 1 is 2. 0 minus 2 is negative 2. Here, negative 2, so 2 times negative 1, negative 2. Negative 2 minus negative 2 is 0. Two times 1 is 2. 1 minus 2, negative 1. 2 times 0 is 0. 1 minus 0 is 1. And notice how we have a 0 here, 0 here. Finally, divide by 2, by negative 2, and by negative 2. So the next operation, row 1 divided by negative 2 replaces row 1. And row 2 divided by negative 2 replaces row 2. And with this, we have 1, 0. Negative 1 divided by negative 2 is 1/2. 1 divided by negative 2 is negative 1/2. 0, 1, negative 1/2, and negative 1/2. You see? So notice how this matrix has the form, the identity with size 2, and a matrix B. The matrix B in this case, that is 1/2, negative 1/2, negative 1/2, and negative 1/2. This one is going to be the inverse of A. And this is the process, right? So let's see other example. Find the inverse of, more complicated this time, 1, 1, 2, negative 2, 0, 4, 3, 1, and negative 2. So again, we create the matrix. We create the matrix, the bigger matrix A, I. Notice that in this case, the size for this matrix is 3 by 3. So I will put here 3 by 3. So I need to put here the identity with size 3. So this is 1, 1, 2, negative 2, 0, 4, 3, 1, negative 2, and here 1, 0, 0, 0, 1, 0, 0, 0, 1. There you have. And the purpose is what? With the row operations to turn this size into, try to turn this side into this side. So let's try to do it. My first pivot is going to be this one. So I think I can perform the operations row 1, no, 2 row 1 plus row 2 will replace row 2. Why? Because I have 1 here. I want to turn this negative 2 into 0, so I multiply times 2. 2 times 1 is 2, plus negative 2 is 0. And then this one, the next operation could be 3 times row 1 minus row 3 will replace row 3. And then after these operations, notice how the row 1 as it is, 1, 1, 2, 1, 0, 0. And now row 2 row 1 plus row 2. 2 times 1 is 2 plus negative 2 is 0. 2 times 1 is 2 plus 0, 2. 2 times 2 is 4 plus 4, 8. 2 times 1 is 2 plus 0 is 2. 2 times 0, 0 plus 1 is 1. And 2 times 0, 0 plus 0, 0. Now I have performed this operation, this one. Now let's do this one. 3 times row 1 minus row 3. 3 times row 1 minus row 3. 3 times 1 is 3 minus 3, 0. 3 times 1 is 3 minus 1 is 2. 3 times 2 is 6. Minus negative 2 is 6 plus 2 is 8. And 3 times 1 is 3 minus 0 is 3. 3 times 0, 0 minus 0, 0. And 3 times 0, 0 minus 1, negative 1. But notice, what do we have here? We have arrived at 2 rows that are equal in the left side of the bigger matrix. By the left side, I mean this side, all of this side. I said before that if at some point when using row operation you see in the left side of this matrix a row with only zeros or 2 rows equal, then stop. The matrix A has no inverse. So in this case, because of this, no inverse. 2 rows equal. No inverse for A. You see? If not, I will have to continue until I can be able to turn all of this into this side. Example. Find the inverse. Of course, it's highly recommendable that you practice this. So beside the exercises that you will have in yeah, I think I will assign this exercise as an assignment that you will have to complete this, right? Yeah, assignment. Find the inverse of this matrix with that shown process. Yeah, you will have, remember, this matrix has size 3 by 3, and you will have to create the bigger matrix, say I3, that is 1, 0, 1, 2, negative 2, negative 1, 3, 0, 0, and 1, 0, 0, 0, 1, 0, 0, 0, 1. You see that? So you will have to, one assignment for this, you will have to show me all the steps when you find the inverse for this one. I won't do it here, okay? You will have to complete this exercise. Anyway, I know in Webboard, in the assignment on Webboard, you will have many exercises like this. Yeah, it's recommendable that you try to do the exercises with this process, but I won't check that on Webboard. But this one here, I will create an announcement to let you know about this. But what is going to be the inverse? The inverse is you can verify. You can use a web page to compute the inverse, right? So let me show you that. The inverse, you can go to this. I recommend this web page that is called Matrix right? This is the name. Or type on Google matrix calculator inverse, and that's all. But this one seems to be well. So how does it work? You can use this to do the assignments on Webwork. Size 3, set the matrix, and then you have to put the entries. The entries for the previous example are 1, 0, 1, 2, negative 2, negative 1, 3, 0, 0, and then calculate. And you see, this is the inverse. 0, 0, let me write it down. So if you want to use another web page, no problem. But notice this is very simple, right, to compute the inverse. So going back to here, there you have the inverse. Now again, I'm going to create an assignment on Blackboard where you will have to upload your work with this one. All right, I will create an announcement to let you know about this. I will let you know the exact minute where the assignment is given, but you will have to find the inverse for this matrix by following these steps, this process. But you already know the answer, right? The answer is this one. So, and for the I know in the assignment on Webwork you have many exercises like this, but you can verify, or you can use the web page to compute the inverse, right? Well, Anyway, you have any question, you can let me know. All right, what else? The video has now 40 minutes, so don't like to make the video so long, but anyway, one particular case is the case 2 by 2. If the matrix A has size 2 by 2 and is given by this, then A has an inverse, or it is invertible, if and only if this number defined by the determinant of A equal to AD minus BC is different from 0. This number is called the determinant. We will study these things later. Determinant of A, AD minus BC, different from 0. And the inverse is given by 1 over determinant of A of the matrix D, negative B, negative C, and A. Example. Find the inverse of 1, 2, 1, 1. So first, notice this has size 2 by 2, so I can apply the previous formula. In this case, we have A equal to 1, B equal to 1, C equal to 1, and D equal to 2. To verify whether this has an inverse or not, compute the determinant. Determinant of A is equal to AD minus BC, and it's going to be equal to 1 times 2 minus 1 times 1. And this leads to 2 minus 1, that is 1, I'm sorry, that is 1. See that? So this is different from 0. This implies the determinant is not 0. So A has an inverse. Now, what is the inverse? The inverse is given by this formula, this one. Notice how this is not exactly the matrix I have here above. No, it's a little different. But first, 1 over the determinant, 1 over the determinant, in this case 1, so 1 over 1 times, be careful here how you put the numbers. First, I need to put D. D is equal to 2. So 2 negative B. Whatever the number B is, it doesn't matter if it is negative, you have to put negative B, multiply it times negative 1. In this case 1, negative 1 times 1 is negative 1. This one here C, negative C. C is 1 as well, so it will be negative 1. And this one is A. The value for A is 1, so I put 1. See? And then you have to multiply with the scalar multiplication the number you have here, this number you have here, times every element. But it's only 1, right? So we have the same. So the inverse is 2, negative 1, negative 1, and 1. You see? So in this case, I think it's simpler to find the inverse when you have a 2 by 2 matrix, right? All right. Applications to systems of equations. Let's see one quick application for this. If A has size n by n and A is invertible, then the system AX equal to B has a solution X equal to A inverse times B. First, all of I know the notation might be confusing. Do not get confused. All of this is all of this this X with this weird symbol. Usually in the book we write this X like in bold. So, but I think it's more complicated to do it here. That's why I put the symbol. This A, X, and this B with this symbol, all of them are matrices. Matrices, all right? So here I'm talking about one equation involving matrices. So this said that you have a system of equation and this matrix A has an inverse, then you can find the solution only multiplying A inverse times B. Of course, I will show you one example. So let's say that we have the system X plus C equal to 1, 2X minus 2Y minus C equal to 1, and 3X equal to 1. We have equation 1, equation 2, and equation 3. All right, first you have to identify, you have to be able that you recognize all of these matrices. Here, the order in which you put the variables is going to be important. So we're going to assume that we have first X, then Y, and then C. These equations must have this order as for their variables or their unknowns. For X, then Y, and then C. And then the matrix A that you're going to create is going to be actually the coefficients in the left side for each equation. According to this, one column for the coefficient of X, one for the coefficients of Y, and one for the coefficient of C. So, for example, for the first equation, what are the coefficients? X, maybe you're saying, well, we don't have any Y. If you don't see an unknown or variable, then assume the coefficient is 0. Then 1x, 0y, 1c. 1, 0, 1. You see? For the second row, 2x, negative 2y, negative 1c. 2, negative 2, negative 1. Here, be careful here. No C, no Y, so it's 3, 1, 1. No, I'm sorry, 3, 0, 0. I'm sorry. What is this? So this is as for this matrix A. What about this X, this matrix X? X always is going to be a column matrix, I mean one column, and it's going to be the matrix of the unknowns or the variables. In this case, in this order, first x, y, and z. And finally, the matrix B is going to be the elements in the right side for each equation. 1, 1, 1. And there you have it. So again, be careful that first the equation is the terms of the equations are in order. I mean, for the x and the y and the z, and then the same here, x, y, z, and x, y, z. And you have this. Once you have identified this, now you need to find the inverse for this one. But notice, this one is the example that you have to do. 1, 0, 1, 1, 0, 1, 2, negative 2, negative 1, 2, negative 2, negative 1, and 3, 0, 0, 3, 0, 0. I know this one has inverse 0, 0, 1/3. 0, 0, 1/3. Negative 1/2, negative 1/2, 1/2. Negative 1/2, negative 1/2, 1/2. 1, 0, negative 1/3. 1, 0, negative 1/3. So again, you first find the matrix A, the matrix X, and the matrix B. Then this system is going to have solution if this matrix has an inverse, and it does in this case. So the inverse, I know, is this one. So to find the solutions, only use the next formula. X is equal to A inverse times B. This one. So you remember we are multiplying matrices. So this A inverse is 0, 0, 1/3, negative 1/2, negative 1/2, 1/2, 1, 0, negative 1/3 times B. What is the matrix B? 1, 1, 1, 1. 1, 1, 1. So all with the multiplication is going to be possible. This is going to be 3 by 3, and this was 3 by 1. So the resulting matrix is, remember, the multiplication is possible, these two numbers are equal, and the resulting matrix is going to have size 3 by 1. So this is going to be only one column with 3 rows. But notice in this case it's simple, because this row 1 times column 1, 0 times 1, plus 0 times 1 plus 1/3. So in this case, when all the elements here are 1, the only thing that I need to do is add the numbers. 0 plus 0 plus 1/3, negative 1/2 plus negative 1/2 plus 1/2. I computed this with row 2 times column 1. This times 1 plus this times 1 plus this times 1. And the same for this one. 1 times 1 plus 0 times 1 plus negative 1/3 times 1. So this becomes 1 plus 0 negative minus 1/3. And then simplify. We have 1/3. Negative 1/2 plus 1/2 is 0, negative 1/2. Negative 1/2, and 1 minus 1/3 is 2/3. So this implies that x is equal to 1/3, y is equal to negative 1/2, and c is equal to 2/3. You see? All right. Oh, properties. I'm going to mention only some properties of inverse matrices. For example, the inverse of the inverse is going to be the original matrix. This one, I think we have to use it in one of the exercises on Webpage. Anyway, you have a problem that you remember, you can let me know. Here we are under the assumption that A and B have inverse. So A and B has an inverse. Then the inverse for the product is equal to B inverse times A inverse. Number 3, a constant times A inverse is equal to 1 over K times A inverse, where K is a real number. And this property, AT has an inverse, and the inverse for the transpose is equal to the transpose of the inverse. Remember, this is the hypothesis, all right? Assume that A and B have inverse. So these properties, again, when I need them in the course, I will let you know. But in general, most of the times, maybe I will only mention them. All right. So I think anyway, you have any question? Remember, you can let me know. I think that's all by now. See you in the next video.